Alright, so we've got a 4 kilogram object. It is moving 8 meters per second west, so mass of 4, velocity of 8, east, sorry. And then 3 is going 6 to the west, so mass of 3, now velocity of 6 in the opposite direction. That would be in negative direction, so I'm going to put a negative on the 6. After the collision, the objects stick together. I've got a 4, and I've got a 3, and I don't know their velocity. First question, what is the momentum of the 3 before the collision? It has a mass of, so first of all, momentum is mass times velocity. It has a mass of 3 and a velocity of negative 6, so it has a momentum of negative 18. What is the momentum of the 4 kilograms? So again, P equals mv, has a mass of 4, a velocity of 8, so that's a momentum of 32. Total momentum would be these two combined. That is a negative, so these add up to a total momentum of 14. Now I'm finding that missing velocity after the collision, so I'm going to plug into my equation, this m1v1, m2v2 equation. 4 times 8 plus 3 times negative 6 equals 4 times I don't know the velocity plus 3 times I don't know the velocity. And these are the same velocity because they are stuck together. So this just becomes 7v. This side is 14. Divide over, that gives me a velocity of 2. And that would be in the east direction because I'm getting a positive value. What is the momentum of the 3 after the collision? So the mass is still 3, but now the velocity is 2, so that's a momentum of 6. Of the 4, still a mass of 4, but now a velocity of 2, so that's a momentum of 8. And that gives me a total momentum of 14, which should be the same because we know total momentum has to be conserved. So the total momentum before should be in the total momentum after. Now, what is the 3 kilograms change in momentum? Well, the actual object, its momentum has changed, obviously, right? It's going 6 this way, now it's going 2 this way. How much did it change by? 2 ways to do this. We can say, okay, it was negative 18 and now it's 6, and do final minus initial. Negative, minusing a negative would be plus, so that would be a change in momentum of 24. You also can just say m delta v, this has a mass of 3. Change of velocity, it came in at negative 6 and now it went to 2, so the change would be 2 minus negative 6. That's 3 times 8, which is also 24. 4 kilograms change in momentum, so it ended with 8 and it started with 32, so the change would be 8 minus 32, which is negative 24. You also can do the m delta v, you'll still get negative 24 right there. And what you should notice is that one is gaining momentum, so it gains momentum. This one loses momentum because the change is positive here and negative here. And you notice that however much this one gained is equal to however much this one lost, which makes sense because, right, that momentum can't just appear or disappear. It has to come from somewhere. So if somebody gives $24, that means the other person got $24. What was the 3 kilograms impulse? Well, remember, impulse is this right here, impulse, and this is change in momentum, and we know that impulse is equal to change in momentum, so if I'm looking for this impulse, well, I don't have force and time, but I do know this guy's change in momentum, 24. Here, again, impulse, same as change in momentum, so the 4 kilograms impulse is the 4 kilograms change in momentum, which is negative 24. The 3 kilograms change in velocity, so the 3 kilograms started with negative 6 and went to 2, so 2 minus negative 6, again we're looking at what the velocity changed by, so it gained 8 meters per second, and the 4 kilograms change in velocity still ended at 2, but this one started at 8, so 2 minus 8 is negative 6 meters per second. Now you'll notice they change by the same momentum, they do not change by the same velocity. Velocity is not conserved. And it should make sense that the 3 kilogram had a little bit more change in its velocity than the 4 kilogram because this one has less mass. So I'm not going to write that. But this one has less mass, so it makes sense that it had a greater change in velocity even though it had the same change in momentum. Alright, a 0.5 kilogram tennis ball is launched from a 1.5 homemade cannon. And the cannon recoils with the speed of 2, so I'm going to say that it goes backwards with the speed of 2, which is a negative 2, and I want to know what is the speed of the tennis ball. So it didn't explicitly tell me that they're at rest, but before the cannon goes backwards, right, that's before the ball is shot, so they're just at rest. It only recoils once the ball is shot, so that's the after picture. So I've got 1.5 times 0 plus 0.5 times 0 equals 1.5 times negative 2 plus 0.5b. This side is 0. This is negative 3 plus 0.5b. Add this one over. That gives me a 3 equals 0.5b. Divide, you get a velocity of 6. And if you didn't make this one negative and you get an answer as negative 6, that's okay. The negative just means these are in opposite directions. And again, it makes sense that this guy has a faster velocity when it goes off. It's going off at 6. This one's going off at 2. Of course, they're opposite directions because they're at rest. Their momentums must cancel out. And this one is faster because their momentums cancel out, not their velocities. Less mass would mean more velocity. We've got the mass of a basketball. It's coming in with a speed of 18 and then it stops. And then I have the change in time and I'm looking for the force. So of course I'm using the force equation, fat math. Force is what I'm looking for. The change in time was 0.1. The mass is 0.53. And the change in velocity, it's 18 going to 0, so the change is negative 18, right? Final minus initial. And then now, I'm just going to divide the 0.1 over, and that gives me a force of negative 95.4 newtons. All right, the next one, we've got a 2 kilogram box attached by a spring to a 5 kilogram box, and they are both initially at rest. So I'm going to have my 2 and my 5 initially at rest. And then the string is cut and applies an impulse, putting them both in motion. The 2 is propelled backwards, so I'm going to make that negative and moves at 2.5. And I want to know what is the velocity of the 5 kilogram. So 2 rest, 5 at rest gives me zeros on the left side. 2 times negative 2.4 after, and I'm looking for the velocity of the 5 after. So this is negative 4.8 plus 5v. And then now I'm going to move the 4.8 over. And I'm going to divide the 5, and that gives me a velocity of 0.96. And you'll notice this one is going off in the opposite direction, which is why it's positive. And you'll notice that it goes off slower. And again, this makes sense because the more mass would go slower. The less mass would go faster. In this case, because they're starting from rest, so their momentums cancel out. But their velocities would be different because they have different masses. We've got a 0.5 kilogram cart moving at 36.4. It collides inelastically with the second cart, which is initially at rest. And together, they stick together and they move off with a velocity of 21.8. And I don't know this guy's mass, so I'm going to call it m. And now we plug into our equation. Now, because they are both moving together, I know both of them each have the velocity of 21.8. So that is this guy's velocity and this guy's velocity. So this goes away. This is 21.8 m. This term is 10.9. And on the left, we've got 7.3. Oh, that's an 18.2. I'm ahead of myself. And now I'm going to subtract the 10.9 over. That gives me 7.3 is 21.8 m. And now I'm going to divide over, and that gives me a mass of 0.33 kilograms. All right, here we've got a 9,230 kilogram truck moving towards a 1,250 kilogram parked car. They entangle together, that means they like stick together and move off together with a velocity of 3, and I'm looking for the truck's initial velocity, so before velocity. So then I've got 9230v plus 1250 is at rest, goes away, equals 9230 times 3 plus this mass also has a velocity of 3. So this goes with the 3 goes with this one and this one. And then these two together plus this one gives me 31,440, and divide the 920 over, and that gives me a velocity of 3.4. And you could have told me that I knew I was going to get more than 3, because we know when this one comes in and picks up this extra mass, it will go slower. So I must have started with at least more than 3, because I got slower and ended at 3. 2 blocks have a spring between them. They're chilling there. After the spring was released, A moves off to the left with a speed of 6, negative because it's to the left. This one's moving to the right with a speed of 3, and I want to know the mass. So 4 times 0 plus m times 0 equals 4 times negative 6 plus m times 3. So that gives me 0 is negative 24 plus 3m. I'm going to add the 24 over, and that gives me what 3m is, so then divide. This is a mass of 8 kilograms. And this should make sense because this one had to be a greater mass because it's going off at a slower velocity. Specifically, see how it has half the velocity? That must come because it has twice the mass. It's twice as heavy, so it'll go half as fast. Two carts colliding. Cart A has a mass of 1.5. It's moving east at 36.5. B has a mass of 0.5 moving west, which means I need to put a negative sign on the 42.8. I want to find the post-collision velocity of B, so it's B that I'm looking for, if cart A moves 10 west. So 0.5 negative because it's west, and now we plug into our equation. These negative signs absolutely matter here because whether you add a positive or a negative, you're going to get a different answer. And it matters that you put the negative 10 with cart A, not cart B. So on the left side, I'm getting 33.5. This is just negative 15 plus 0.5V. I'm going to add the 15 over. I get 48.5 as 0.5V. Divide, I get a velocity of 97. So bumped it, and then it got super fast this way. Carts initially at rest. The diagram shows after they are pushed apart, the mass of cart B is 3 times the mass of A. So I'm going to call this one M and this one 3M. And I'm looking for this missing velocity. Now, because this is multiple choice, you actually can get the answer without solving it. We know that they're both going to go off. I know that this one is heavier, so it's going to be a less speed. I know that it can't be 0.33 because it's going slower. It can't be more because it's going slower. And it's not 0, right? If I just had this one moved and this one stayed at rest, then momentum wouldn't be conserved because I need the momentums to cancel out. So it has to be this one because it can't be at rest. Now to actually do it, right? So you're saying this is starting at 0, and then you've got m times 0.33 plus 3m times I'm looking for the velocity. If you subtract over 3mv to get b by itself, you divide the 3m over, and you'll notice m's cancel out, you just get negative 0.11. I don't know why I put a negative, that would be negative, my bad. Alright, two pucks have a string between them, they're initially held at rest. When the pucks are then released at the same time, puck 1 that has 3 times the mass of puck 2, what do we know about their momentums? I know they're going to go apart like this. I know I'm going to start with velocities. They're not going to go at the same velocity. M is going to go faster, so puck 2 is going to be faster because it has less mass. And that means puck 3 would then go slower. So I'm going to say slower and faster. Specifically, this is going to be 3 times faster than this one because it has 1/3 the mass. And now about their momentum. So think about, this is this is the special case where everything is at rest at first, which means the total momentum is 0. Now here, because momentum has to be conserved, I still need a total momentum of 0. The only way you have two objects moving and they add up to a total of 0 is if their momentums cancel out. So here, their momentums must be the same or equal, but they are also opposite, right? One would be to the right, one would be to the left. So equal but opposite or same but opposite because they cancel out to keep a total momentum of 0. So that will not always be the case. It is only the case here because I am starting both of them from rest, which is a total of 0, which means if you still have a total of 0, the two must cancel out to 0. So an example, I've got a 0.5 kilogram bullet and I've got a 4 kilogram rifle initially at rest. If the bullet leaves, I don't know the velocity, but I know this guy has a momentum of 20. And I want to know what is the momentum of this guy. I know it's going to have a slower velocity. I'm not asking about the velocity. I'm asking what this guy's momentum would be. So think about, the total momentum was 0. Momentum has to be conserved, so the total momentum still has to be 0. If this one has 20, this one would have to have negative 20. So it would have to cancel out. which is exactly what we said. These two, right, similar situation, their momentums have to be equal but opposite. If one is 20, the other is negative 20. Finding momentum, which one has more momentum? You literally multiply and find the momentum. So this one has 75, this one's got 50, this one's got 100, this one's 75. So the most momentum is C. The object that would be the hardest to stop. So the one that's the hardest to stop is the one with the more momentum, right? More mass and coming faster is going to be harder for it to stop, so that would be C here. The one that would be easiest to stop is the one with least momentum, which would be B. A and B. So it says that A is in motion. It's coming over here. This guy's at rest. Then they hit and they're going to stick together, and now they're going to go over, and these two together share the same speed. Now, if this is coming in with a speed of, I don't know, let's call it B, I know when they stick together, their speed is not the same now as it was before. We know that this guy is going to get slower, so I'm going to say slower. That doesn't look favorable, slower, but that's okay. I know this guy is going to get slower when he picks up his friend, because he's now giving some of his momentum away. He's sharing momentum with more mass, so it'll go slower than before. So that means A will slow down, definitely, and B was at rest and now he's moving, so B just got faster. A, gain or lose momentum. Well, we just said A slows down, so that means it's losing momentum, and B got faster, which means he's gaining momentum. And this makes sense, because if A is losing, that means A is giving momentum to B, right? If we think about the money, that's like him having $10, this guy having $0, and then he's like, okay, I'll give you some. Now I have 5, now you have 5. He lost 5, he gained 5. He got slower, he got faster. A 1 kilogram laboratory cart is moving with a velocity of 0.5 east. So 1 going 0.5, the similar cart initially at rest. After the collision, the two move off together at the velocity of 0.25. What do we know about the total momentum? Okay, it stays the same because momentum is conserved. Total momentum is conserved. Right here we've got two masses, same force, same duration of time. So I'm going to talk about this equation. And I know F is the same for both and time is the same for both. Change in momentum is m delta v. Right now I do know this one has a bigger mass, but I don't know about their velocities. So I'm going to jump to impulse. Impulse is F delta t. They have the same F, they have the same t, so they have to have the same impulse. Now, this is your impulse, but see how it's equal to change in momentum? So if this side is the same, then their m delta v side has to be the same. So they have to have the same change in momentum. Now, they do not have to have the same change of velocity. I want which one has a greater change of velocity. So think about, if they still have the same impulse, if this and this is equal on this side, I need a bigger velocity to be balanced out with a smaller mass. So 10 is smaller mass, so B would be the one that has a greater velocity. And this should make sense, like just common sense wise, right? If I have two objects, I push them with the same force for the same amount of time, then the smaller mass is going to be faster after that than the heavier mass would be. Force of 20 newtons exerted on a cart for 10 seconds. For what period of time must a 50 newton force act to produce the same change in momentum? So change in momentum is m delta v. I don't have m delta v, but I know that's also equal to the f delta t. So think about, if I have a force of 20 for 10 seconds, see how that's an impulse of, or change of momentum of 200. If I still want the 200, but now I have a 50 newton force, you need to figure out what time would be needed to still get to 200. Divide 50 over, and you get, I can do this, 4. Okay, now, if you didn't do the math, you probably could have crossed off some of these, because if you think about, okay, I have this force, and now I have a bigger force. I still want the same end result. If I have a bigger force, that would take less time than before, so you can at least cross off this one, and, oh wait, no, you can't cross off this one. You can cross off this one. I guess that didn't really help you that much. You still have to actually calculate it to get how much smaller. Alright, suppose someone fires a bullet from a gun. The speed of the bullet leaving the muzzle will be the same as the speed leaving the gun. Not usually. Usually the bullet goes way faster than the gun. The only reason these would both go off at the same speed is if they were the same mass. Normally, this one would go much faster and this one would go much slower because the bullet has less mass and the gun has more mass. The only reason they'd be going off the same speed is if their masses were equal. The firing of a bullet by a rifle causes the rifle to recoil backwards. The speed is smaller, so the rifle speed, really just what we were talking about, the rifle speed is much slower than the bullet speed because the rifle has a much greater mass. A wad of chewing gum is moving to the right. It's got a momentum of 1 when it collides with a heavy box initially at rest. They stick together and then they're set in motion with a combined momentum of, well, think about, my total momentum first was the 1 with 0, so 1. My total momentum after still has to be 1. The velocity is going to be less, right? It's going to give some of its momentum away, but the total amount of momentum still be the same. So it's just going slower, but I now have more mass, so it's still the same total momentum. I've got 0.5 kilograms, I've got a force, I've got a time, and I've got another mass, another force, and another time for cart 2. I'm going to kind of separate it. Which cart has a greater change of momentum? Change of momentum is m delta v, or you can also use f delta t. It doesn't matter. In this case, I have both, so I'm going to find change of momentum by f delta t. For cart 1, that's just 1. For cart 2, that's 2 times 0.5, which is also 1. So you'll notice that they actually have the same change in momentum. This one has a larger force, but it also has it for less time. This one has a smaller force, but it has it for longer, so that ends up balancing out, so they still have the same impulse and the same change in momentum. Now, which has the greatest velocity? Think about, they have the same impulse, right? But if your m delta v is the same, the delta v is only the same if the mass is equal. Here, if you look, I'm going to actually plug in f delta t equals m delta v. We've got a force of 1, time of 1, mass of 0.5 delta v. Divide over, that gives me a delta v of 2. Here, I've got the 2.5 equals mass of 0.25 delta v. 1 divided by 0.25 is change of velocity of 4. So cart 2 has a greater change in velocity, and that makes sense. If you're applying the same impulse, you get the same change of momentum, but this one has less mass. It should have a greater speed after change of velocity more. Okay, true or false? Two objects of different mass moving at different speeds, the more massive will always mean the greatest momentum. That is false. More massive only means more momentum if their velocities are the same. If they're not the same, then you have to actually have the two because they both matter, right? Both mass and velocity matter for momentum. A force of 100 newtons acting for 1 second would provide an equivalent impulse as 5 newtons acting for 2 seconds. Well, impulse is just force times time. 100 times 0.1 is 10. 5 times 2 is 10. So yeah, that's true. In a collision, net impulse experienced by an object is equal to its momentum change. Impulse equal to momentum change, right? We know impulse is the same as change in momentum, so that is true. Kilogram meters per second is equivalent to the units on impulse, Newton seconds. Think about F delta T equals M delta V. Newton is force is Newton, time is seconds, and that's equal mass, which is kilograms, velocity, which is meters per second. So yeah, those must be equivalent because the equation is equal. While individual objects may change their velocity, the overall or total velocity of colliding objects is conserved. That is not true. There is no law in the universe saying velocity is conserved. Momentum has to be conserved, but not velocity. In a collision, if one object's momentum increases, the other objects must decrease. Yes, that is absolutely true, because the total momentum must stay the same. If one object is getting more, that came at a loss of something else. So think about the money example, right? If somebody else got $5 more, that means somebody lost $5.